Hi there. In this short video, I'm going to talk to you about the Nash equilibrium, what it is and how to find it, and illustrate the famous prisoner's dilemma. But before I do that, allow me to clarify some basic terms that are going to be useful throughout this video. First, we are going to presume that all players involved in a game are rational, which is to say that each individually looks forward to maximize his or her individual payoff. Secondly, we are analyzing a static game, which is to say that moves through the game are simultaneously, so no one can know in advance what the strategy of his or her opponent is. We are also looking at perfect information games, and by that I mean that all players know all possible outcomes of all other players. So this also is an important key term in order to fully appreciate and understand how game theory in this particular case operates. So we're playing at a non-cooperative, static, with perfect information game where all players are rational. Here I have represented the famous prisoner's dilemma, and the story goes like this. Two players are caught up by the police. They are suspected to have robbed a bank, and but the police doesn't have enough information, so they are separated and interrogated in two different rooms, a non-cooperative game, and also to them are presented the full set of information that they need in order to play a decent game theory. So here I have represented the game, and basically we have two players, player A and player B, and each of the player has two possible strategies to adopt. C stands for cooperate, which is to say in this case to cooperate with the police, and usually when you cooperate with the police some advantage is going to happen, so we all know that from CSI. And not to cooperate, which is to say stay faithful or not to betray his or her opponent. And these are the four different outcomes. By convention, we are going to assume that the first number in each cell refers to the payoff of player A, and whereas the second number refers to the payoff of player B. So for example, if player A chooses not to cooperate along with player B not to cooperate, this 4 stands for the payoff of player A, and in this case both players have the same amount of payoff, and we are going to assume that they robbed the bank and they are going to split the money in half, and so they have robbed 8 million pounds or dollars or whatever. So in order to fully analyze all the different outcomes, we have to think through all individual strategy that each individual or player has it at its disposal. So let's think about what player A might think as its initial thought. So he might think, you know what, I'm not going to confess. Therefore he immediately chooses to not to confess. So this part of the table is not going to be useful for this kind of decision. So if he does choose not to confess, for player B remains two different possible solutions to the game. He either not confess along with his opponent and both get the 4-4 situation, or he has to confess, he confesses and he gets the 8 million, and the other, which is to say player A, gets -8. You can think about -8 as he loses $8 million or 8 years in prison or whatever. So if you remember, we said that rational means look forward to maximize his payoff. So player B, in the case of player A, not confesses, player B is always going to choose to confess. So this is one example of how the thinking should allow. So therefore, if player A knows that player B is rational, and he is also rational, he is never going to choose not to confess. And so therefore, he will eventually end up confessing. This kind of situation and the confess strategy represents a dominant strategy. Therefore, considering that the situation is symmetrical, on the other hand, B is going to cooperate along with A because both makes the same sort of reasoning. So in the presence of a dominant strategy, in this case both players are going to cooperate, and this constitutes a Nash equilibrium, but it's not the full idea, because the presence of a dominant strategy, and a dominant strategy is the strategy that guarantees the higher payoff independently of what the other player does, it represents a Nash equilibrium. But what a Nash equilibrium is just basically the solution that no player can do better unilaterally. So from an individual perspective, cannot do better by changing his strategy. So in this case, player A cannot do better by changing his strategy from confess to not confess. So just that, just a solution where no one is whatsoever incentivized or interested to change the strategy adopted. And notice, to a third party, this might seem as illogical and not rational solution, but unfortunately this is what happens. And notice that this has nothing to do with a solution, a Pareto efficient solution. That's the Pareto efficient solution is another kind of equilibrium, and in that solution is the situation in which it is impossible to make anyone better off without making at least one individual worse off. So is another perspective. So how to find the Nash equilibrium, and in situations where there are no dominant strategies. And I'll represent a different game, and I'll go through the reasoning required to find the Nash equilibrium. So in this new situation, I have represented a game in which two players have three individual possible solution strategies at their disposal. But before going into details about what the solution to this particular problem is, let's imagine a situation in which two or more players have a finite number of strategies, so on. So there is this mechanism that if I know that he will choose that kind of strategy, my best response would be this. So it looks like this is endless, but if the game has a Nash equilibrium, eventually players will eventually find that situation and will stick to that. And by that I mean, once the Nash equilibrium is identified, no individual player has any interest into changing his strategy, because that initiate the whole process of finding again the solution. So in this particular case, let's apply the kind of reasoning to this particular case, and let us find the Nash equilibrium. A useful tool or tip for finding the Nash equilibrium is this. You go through the reasoning of each player, imagining each situation, and you are going to underlie the best solution to a particular strategy. So for example, player A in this case, if he adopts strategy number 3, he is going to underlie the best response from his opponents. So in this case, I'm going to underlie number 7, because if A chooses the third strategy, player B, considering it rational, he will not choose B3 because his payoff will be 6, nor he will be adopting strategy B2 because his payoff will be 1, but if he's rational, he will choose strategy numbered in this case B1. So we are going to underline 7. In the second case, if player A chooses the second strategy, in this case you can understand that we are going to underline the number 9, because this represents the best response from player B if he thinks that player A will adopt strategy number 2. And also the same kind of reasoning will apply to strategy number 1. So in this case we are going to underline 5. So the exact same thing has to be applied to player B. So player B thinks, what's the best solution of player A if I chooses to play B1? And we can see it from the highest possible payoff for player A is 6 by choosing strategy number 2. What's the best possible outcome for player A if B chooses B2? Obviously we can see it from here, from these 3 numbers. It is represented by number 8. What's the best solution for player A if player B chooses B3? Is not 7, not 2, but 9. So the only cell underlined in both payoffs, A also B, is that represents a Nash equilibrium. So basically this is the Nash equilibrium in a nutshell. Apply this for multiple players, for multiple strategies. Add the ingredient of non-rationality, add the possibility of repeating the game, and consider even the possibility of cooperating between people. Also add the possibility or the case in which perfect information is not possible, and you'll get the idea and the complexity of the world outside and the study of economics in which scientists are trying to find out and to reduce the complexity and to apply different formulas in different situations and strategies to optimize solutions. So that's it. I chose so number okay, and 8. So notice that the only the strategy the strategy A1. Sorry about that. Oh shit. Ah, fuck off.